Hey everyone, I'm Julian, your Biology 2600 lab instructor, and in this video I'm going to cover the material for Lab 6, random sampling. So last week we looked at how different populations grow. This week we're going to build on that and look at how you actually get the data to determine if a population is growing, decreasing, or not changing at all. So the purpose of this lab is to provide an overview of random sampling and to highlight the importance of sampling design in representing a larger study area. This lab is spread over 2 weeks because in a normal semester, in the first week, students will actually go out to the field to do their sampling, and then in the second week, they will do their calculations and their write-up. So before watching this video, please make sure you read the Lab 6 file and also look at Dr. Leroux's Week 3 lectures for the background on scientific method and experimental design, and his a little clip in his Week 8 lecture, which introduces some of the statistics that we're going to be looking at. So here's an outline of what I'm going to talk about in this video. So I'm going to start with the random sampling background, and this will include a little example. Then I'm going to talk about the experimental setup for this specific lab. I'm going to run through the calculations using some made-up numbers, and this includes the t-test. Then we're going to talk about species richness and accumulation and how to make those graphs. And then finally, the scientific write-up. So we're going to start with the random sampling background. So in nature, some populations are either really large or just impractical to measure, or it's just really expensive or time-consuming to measure all of the individuals or organisms within a population. So to overcome this, scientists take smaller samples from that entire population and try to extrapolate the data from a smaller sample to the larger population. So the definition of a sample is a selection of objects or observations taken from the population of interest. So two very important things that you must remember or try to accomplish when taking a sample is that it should be unbiased. So each object or organism should be equally likely to be selected. And your sample should be representative of the entire population. So I'm going to go through a little example which illustrates these points. So let's say that I was going to give you guys 5 billion points. And just for those of you that don't know, these points can't get you any marks or can't trade them in for a cash value. But students seem to like the idea, so I'll keep giving them out. So 5 billion points, if you could estimate the population or the size of, the number of tulips and daisies in this field. Now, for the sake of this example, let's pretend that this field was actually significantly larger than it is. And let's say that I happen to give you another really hard R lab, and you just never had the time to do it. So one thing you can do is take a smaller sample of this and extrapolate to the entire population. In order to do this, we make a grid like so, and then you'd randomly pick quadrants within this grid, count the organisms there, and extrapolate to the larger population. So let's say that you happen to choose these 5 quadrants here. So the problem with this is that this sample would be biased. So what that means is you don't have an equal likelihood of picking both tulips and daisies, so the 2 organisms in this population, if you pick these 5 quadrants. So you would need to, so that's one issue that could come up. So let's say we picked these 5 quadrants. So this population, or this sample now is unbiased because you have a chance of getting daisies, you have a chance of getting tulips. However, this population wouldn't be representative. So just by taking a quick look, you can see that there's a lot more daisies than there is tulips. But in this case, if we count them, the ratio would be 2 daisies to 1 tulip. And that is not representative of the entire population. So the point of this example is that you get an idea that it's actually hard to get a completely random sample that is unbiased and representative of the population. So one thing we can do is just increase the number of random samples that we're taking. And so the more and more samples that we take, the more statistical power that they will have, and the more and more chance that they will be unbiased and have a likelihood of being representative of the entire population. Now, there's going to be a fine balance there because once you get to a certain point, you might as well count all of the individuals in the population. So we're going to talk about what size is appropriate in this lab. So that covers the random sampling background. Next, we're going to move to the experimental design for this specific lab. So the first thing I'm going to do is show you where the site is. So this is a large portion of Memorial University's St. John's campus, science building, new core science facility, and then we're going to travel to Gillies Road, which is just down the road from Mon Botanical Gardens. So it is right here, and our plot area is just for the small trail. So if we shift over there, this is it. So this image is obviously low resolution and fairly old. So I'm going to give you a new one. So here is a more recent and higher resolution image of the plot area. So the first thing that was done was a grid was made, which looks like this. So this was normally, this would normally be made out of using rope, but it's easier to see it this way. So each of these quadrants is 5 meters by 5 meters, and there's a total of 25 quadrants in total. Next step was to divide each of those quadrants into 4. So now each of the smaller ones was 2.5 by 2.5, and they were systematically numbered from 1 to 100, as you can see here. And so the purpose of this was to randomly assign students 4 plot areas. So using a random number generator, they were given random numbers, 4 of them, where they did their sampling. So let's say they were given 11 to start with. So they would go to this quadrant right here, they would do their tree and shrub sampling, and then they would pick an area within that was 1 meter by 1 meter, and they would do their herbaceous plant sampling in that. And then they would do 3 more of both of these to have a total of 4, and that would be where you get your sample data from. All right, so moving along, now we're going to cover the calculations. So I'm not going to lie to you, when I first skimmed over this lab, I did almost throw up. It was definitely a bit overwhelming, and there is a bit of gymnastics involved. So to make it easier for you, it's actually not that bad once you get into it. But just to make it easier for you to follow along, I've created these summary flowcharts. So there's two types of organisms that were surveyed. So trees and shrubs, which are done up here, and herbaceous plants, which are done up here. And then you have 2 samples for each. So the student sample and then the class sample. So I'm going to go through the calculations in this one here, just to show you how to do it, and then you can do it for the other one after. So we're going to start with table 1, which is the tree and shrub plots. So this is your data here. your sample data. So listed here are the tree and shrubs plants that were found in the 4 plots that students surveyed. So these are obviously abbreviations. If you want to find out what they actually stand for, you can go to the abbreviation file in Brightspace. And also, there's another file which actually shows you pictures of all of these organisms, which I think it'll be useful if you took a look at that. Also on Brightspace, so feel free to take a look at that. So the first step is just getting the total number of species. So you just count these and you write in the numbers, and here are your answers. So I'm just gonna minimize or make that little area smaller. And so then I can talk about the descriptive statistics. So we're going to perform a number of descriptive statistics, and Dr. LaRue covers some of these in his week 8, at the beginning of his week 8 lecture. So descriptive statistics allow us to describe the data, but they also allow us to compare different types of data. So the first thing we're going to cover is the mean. And the mean is just the overall, it gives you an idea of the position of the data, or specifically the center of the data. So if we do a little distribution plot like this, so down here you have the number of plants that were observed, and here you have the number of plants, number of times they were observed. So for example, so using these numbers up here, 5 wasn't observed, so that's 0. 6 was seen once. 7 wasn't. 8, 9, and 10. 8, 9, and 10 were observed once, and 11 wasn't observed. So the reason that this is, I plotted this way is just so I could show you how these descriptive statistics work. So if you were to take an average of this, or the mean, you would find out that the mean is 8.5. Or in other words, the center of the data is right here. So if these numbers change, this mean would change correspondingly. So it could either shift left, shift right, or not shift at all. But the idea is that it will always be in the center of the data. And so another way to describe this is that if someone asked you, what is the typical number of plants found in each of these plots, and you were to say 8.5, that would be correct. So the other descriptive statistic that we're going to talk about that describes data is the spread. So as opposed to the center, we're going to describe the spread of the data. So this was from the previous page, and the spread is how far apart the points are that you have. So for this one, the highest value observed is 10, the lowest is 6, so we have a spread of 4. So if we have a different set of samples, so 2, 9, 11, and 5, we plot those, now we can see that the data goes from 2 to 11. So the spread here would be 9. So these are just quick numbers to describe the spread, but the point is you can see that this data is much more distributed and much widely distributed compared to this one. So we did that. Now we're going to go to table 3A. So using your information from table 1, we're going to put that in here. And so in terms of describing the spread of the data, the actual statistics that we're going to use are variance, standard deviation, and standard error. So these numbers here are just your means. So we put those in. And so as you can see, these are not the ones we had before. So I don't want to do the calculations for you. I just want to show you how to do them. So these are some random numbers that I picked. Sum is just adding these up. That's pretty straightforward. And the mean is dividing the sum by 4. And that, in this case, with these random numbers, would be 6.5. Your next step, oh, got excited. Your next step is to take the mean away from each of the individual values that you have here. So 5 minus 6.5 is 1.5, 6 minus 6.5 is 0.5, and so on. And the next step is just to square all of those values. So 1.5 squares, 2.25. SSA is the sum of the squares, so you add these up and you get a value of 5. So I'll also mention the n here represents the number of samples, so in this case it's 4. Degrees of freedom is another variable. It's simply the population size, so n minus 1. So in this case 3. So to calculate the variance, so this equation looks scary, but you have most of it actually done. So the numerator here represents the sum of squares, so it's just this value here. And the denominator is your degrees of freedom, or your n minus 1, which is 3. So 5 divided by 3 gives you 1.67. And then all we're going to do is take the square root of that to get your standard deviation. And the square root of 1.67 is 1.29. And lastly, you do the standard deviation divided by the square root of n, which is 4. So 1.29 divided by 2 will give you this value here. So once you get started, it's actually not that bad. So we've done everything here. Next step is to do the exact same steps as statistics for the class data. So I'm not going to go through those. I'm just going to give you some random numbers that I pick. The equations are the same. You do them the exact same way. So here are your numbers. So we have that. Now that we have descriptive stats for the student and class data, we're going to compare them. And to do that, you're going to start with your pool of variance, which is this equation here. So I'm not going to plug in the values, but I'll tell you where to get them. So from table 3A, which is your student data, you've already calculated your sum of squares, and you already have your degrees of freedom. And from table 3B, you have your class sum of squares and your class degrees of freedom. So you just add the top, add the bottom, and divide. And so this is your pooled variance, your standard error of the means. It's calculated using this equation. So the numbers up here are the ones that we just calculated right here. And all you do is simply divide by your population for your student data, which is 4, and your population size for your class data, which is 20. And that shows you where to get those values. So the last thing that we do, last equation, is calculate our t-value. So from table 3A, you can get your mean for your student data. Table 3B, you can get your mean for your class data. These lines on either side indicate absolute value. So if this number happens to be negative, you just pretend it's not. It's always going to be a positive value. And you divide it by your standard error of the means that we calculated on the previous slide. So you also want to get your total degrees of freedom. So your degrees of freedom for your student was 3, plus your degrees of freedom from your class, 19, and that's 22. And this is table 5 in your lab file, which shows you your critical t-value. So using your degrees of freedom, you go down to 22, and your critical t-value is 1.717. So I'm going to give you the 2 possible options that can occur here. So in scenario 1, let's say that our calculated t-value from this equation was 2.27. So 2.27 is obviously larger than this. So what that means is the student and the class data are different. In other words, the student data is not representative of the class data. So that's important because you're going to include that conclusion in your report based on your t-value. And for scenario 2, let's say your calculated t-value was 0.27. And so this is obviously lower than your critical t. And what this means is that your student and class data are not different, or in other words, your student data is an actual representative random sample of your class data. again, that's important. You're going to be including one of these in your report. So we have done everything here. Next, we're just going to plot some graphs. So if you want to graphically display your means, you can do that. So this is the mean for your student data. This is the mean for your class data. And I think these are actually, I don't know if they're actually the correct values. I don't think they are. And the error bars here are specifically the standard error. So this just gives you a graphic representation of what the means look like, so you can graphically or visually see how your student data sample compares to your class data sample. So the thing about this is that it's also referred to as species richness. So sounds fancy, but it's just the number of species in a community. So and this is important actually because it allows you to understand community structure. So um, knowing the number of species or the species richness in a community from one time point to another allows us to understand how it changes. So let's say it's undergoing primary succession or secondary succession, or there's been a natural disaster, or you just want to look at how communities are changing as a result of climate change. Species richness would be the way to do it. So you will actually be making two of these graphs, one for your tree and shrub data and one for your herbaceous plant data. So the last thing we're going to do is look at how um, your sample size affects the estimates of species richness. So this will be done by making a species accumulation curve. So if we go back to table 2B, I believe, you will see that, well, you should already have the total number calculated, so that's easy. You just count the total number for each column and you're ready here. But there's also the cumulative number for new species. So I'm gonna show you how to do that now. So for the first column, it's pretty straightforward. It's going to be the exact same. So you have 5 species up here, and all of these are new because we're just starting. And then the species that occur here, we're going to eliminate them from the rest and see how many more new species are added with each column. So taking SG, so this occurs here, so you want to eliminate it everywhere else that occurs thereafter. And so you're going to end up doing this for everything else. So the next one is GGR. You're going to eliminate everywhere you see GGR. So here and here. TG, same thing. Cross those out. RGR, so a couple here, and so on. And PS, bunch of those, so you cross them out. So we got the number of species here. And now we're going to add species as we go. So you have 1 new species in this column, so you add up to this, so you get 6. Got excited, you get 6. So I'm not going to show you this, but what you would do is cross out PO everywhere after because it occurs here, so it's no longer a new species. This column, everything's crossed out, so it stays a 6. This one stays a 6. DS is 1 new one, so you'd add that, you'd get 7, and don't forget to cross out DS, and you keep going like that. So once you have that completed, you just put the values in Excel. So your plot number from 1 to 20 and your cumulative species. So these are just random numbers to give a certain graph, so I can talk about the options or different types of things that can happen. You would obviously put in your values here. So if you were to plot this on a dot plot, you'd end up getting like something like this. And so what we can see here is that your curve actually flattens out. So probably at around this point here, which is 7, I believe, it ends up being flat. So what you would say for this curve is that the curve flattens. So you have an estimate of the number of plots required to capture species richness. So the estimate would be after you take samples from 7 plots, you have captured the species richness for this area. What that means is you no longer get an increase in species. So just by sampling 7 plots, um, you have captured the species richness. So this is an ideal situation. Um, if your curve doesn't flatten out, so this is just some sample data which shows you a curve that doesn't flatten out, you can no longer say this. So in this case, if your data, when you plot it, looks more like this one, you'd say the curve doesn't flatten out. So 20 plots is not enough to capture the species richness for this area, which is written down here. And so you suggest that more plots are needed. So that covers all your calculations and graphs and essentially results. The last thing is your write-up. So I'm gonna get out of this, bring that up. So, and this is in your actual lab file. So your lab sections you're gonna include are here. So title, make sure you're specific, what was done, when and where. Introduction should be about 200 to 300 words, not counting your hypothesis. So you're going to explain the concept and importance of random sampling, and you want to include some sources. So these sources can either be, so at least 2 sources. So there's no specific requirement on type of study or year or anything like that, just any 2 reputable sources from textbook, journal, university, research institute, whatever you want. And they have to be on, they can be either on general types of studies about random sampling or specific study on random sampling, just something that kind of supports what you're saying here about the concept and or the importance of random sampling. And you should finish off with your statement on the purpose of the lab. So you're going to have 2 hypotheses at the end of your introduction. Hypotheses are going to be based on these 2 problems here. So if you never had me from in first year, and if you don't remember how to make a hypothesis, the easiest way to do it is to just turn your problem into a statement. So is the student sample data on trees, shrubs, and herbaceous plants representative of class sample data? All you do is get rid of the and say the student sample data on trees, shrubs, and herbaceous plants is or isn't representative of the class data. All you have to do, same thing down here, was the class sampling enough to capture? You just say the class sampling was or was not enough to capture the full species richness of the study site. And so I'm going to talk more about those in a second, but in terms of grading your hypotheses, pretty straightforward. So for your methods, just refer to this lab handout. So in terms of your results, you're going to include the 4 tables, completed 4 tables, and all the calculations that are on pages 9 to 19 in an appendix section at the back of your lab. In the actual results section, you're going to start with your calculated t-values versus your critical t's. And so there should be 2 sets of these, one for trees and shrubs and one for your herbaceous plants, and then a statement whether or not the student samples were significantly different from the class. Also, you're going to include your 2 bar graphs for your species richness. So the example of this is in figure 3. So it looks like this. So these are your means and the bars are your standard error. And you're also going to have 2 dot plots of your species accumulation curves. So example for that is figure 4, which looks something like this. So your curve may flatten, it may not. Um, it's part of the excitement. See what happens. But anyway, it should go here. Um, and so you're going to have two of these graphs as well, two of both of these graphs, so 4 graphs in total, 2 bar graphs, 2 dot plots. Um, one side is going to be for trees and shrubs, and the other is for your herbaceous plants. And you're going to finish off your results section with a written summary of trends. Make sure you don't explain anything here. There is lots of time and space to do that in the discussion. So in terms of your discussion, you are going to begin by saying whether or not your results support your hypotheses and then explain why in detail. So I'm going to specifically show you what that means. So I already mentioned that there's one of two possible outcomes here. Either your t-value is going to be lower or higher than your critical t. So if it's lower, your student and class data are not different from each other. And the other way to say this is that your student data is representative of the class. So just want to remind you what representative means here. So if you say the student data is representative, that means all of the plants that were found in the student sample data are a true representation, so they are equal to the proportion of plants in the class. So you kind of think about what this means. So student data included 4 samples, and the class data included 20 of these samples. So if they are the same, um, what you can say, or how you can summarize this, is that the plants in this plot are randomly distributed. And that is why the student data is able to be an accurate representation of the class data. And so the opposite of this, so let's say your t-value was higher than your critical t, which means samples are different and your student data is not representative of your class. So this is the opposite scenario. So what this would mean is that plants were distributed unevenly. So let's say in this area here, you had a patch of trees which didn't exist anywhere else. So your student sample had to include one of these, then they would not be able, or sorry, didn't include one of these, then they would not be able to properly represent the entire um, class data, or so it would not be representative. So this is one possible explanation why your student and class data are different. And the other one is much more simple. Excuse me. It may just be that 4 samples was not enough to accurately depict the 20 samples in the class data. So the other hypothesis um, refers to the species accumulation. And in this case, you're going to have one of two possibilities again. So either your curve flattens, as is the case here. And so what that means, or sorry, or your curve doesn't flatten, this here. And so you're going to comment on that. I already explained this in detail, so I'm not going to go through it again. But I will just kind of put things in perspective for you. So in terms of the student data, the trees and shrubs that were sampled represent approximately 4% of all of the data here. So student data does 4 plots, and there's 100 plots here, so 4%. In terms of the herbaceous, it was less than a quarter of each of these plots, so it's less than 1% in total. The class data represents 20% of this entire plot, and in terms of trees and in terms of herbaceous plants, less than 5. So that's just something to keep in mind. So you don't have to actually include these numbers in your report, but it kind of gives you an idea of why the curve might flatten or why it might not flatten. So we're going to go back to the Word file. All right, so that's the first part of your discussion. And then there's a list of questions here that you want to address. So make sure you do this in paragraph form. And so you could dedicate a paragraph to each one, or you can put them all in the same paragraph, just not jot out form. So one of them is, why is measuring species richness important? So I talked about that earlier, so I won't say it. Um, Second one is, do you think class samples are representative of the true diversity? And so is your answer for shrubs, trees and shrubs versus herbaceous plants different? So um, this is where you can kind of factor in those numbers. So the class samples represent approximately 20% of the shrubs and less than 5% of the herbaceous plants. Um, the other thing to keep in mind here is that um, one of the obvious differences that's particularly relevant here is that shrubs and trees are going to have woody stems, and that means they're actually going to be there year after year. They just get bigger. Whereas herbaceous plants have a growing season every year. So, considering that it is November-ish, some of those herbaceous plants may have already um, had, may already be past their growing season. So they may not occur at all, or they may occur in some sections. So if they grow in like sunny sections, they may only occur there. The shaded ones may have died off for this year because it's after getting colder. So consider those things there. If you want to sample mature forest, how would you change the methodology? So one thing I didn't mention is that the quadrant sizes weren't actually picked by random. They're set up to correlate with the size of the organisms or the plants that exist at the site. So based on the size of the quadrant, you can get a decent sample of the plants at this site. Uh, and that's because these plants are relatively new, so they're relatively small. So a plot area of 5 meters by 5 meters or 2.5 by 2.5 is appropriate. So if you're sampling mature forest, the obvious difference is that your plants are going to be much larger. And if your plants are much larger, you should increase the size of your quadrant in order, I mean, you don't just want to have one tree in your quadrant. That wouldn't give you a very good representative sample. Um, Next one is, if a stream ran through your sampling area, how would you adapt your methodology? So, two things to consider here. One is that if you have a stream, you're going to have completely different organisms than you would anywhere else. And that is related to the fact that depending on what samples the student data would, where the student data samples would be, they may not be representative. So I'm not going to say more about that, except that this is actually discussed in detail in those pages that are referenced in your textbook at the beginning of this lab. So make sure you read that section. It's, I believe it's called Sampling Communities. And you're going to finish off by talking about some sources of error or how you can improve the methodology in this experiment. And so these sources of error should be not something that you mention up here. And of course, make sure you you have a list of literature cited material using the journal Ecology Letters format. So this is referring to your um, the references that you use up here. And when you use the reference up here, make sure you remember to cite in-text citations.